Okay, perfect. So, how would I put this? Welcome again to the class, and actually, we're really close to finishing. I figured that the remaining topics really are bonus, good to know topics actually, but they're really useful, especially when you start working in some company or some research project, because these methods, uh, the way I'm gonna treat them is that like memory hierarchy and caches, they are well studied methods already, and they're very useful in case you need to design something that needs the performance improvements of memory hierarchy. Okay. So today it's a nice lesson because there's a little bit of life lesson about it, which has something to do about learning. So yeah, the goal for today is to learn the basic memory hierarchy. Why do we need the memory hierarchy? A basic calculation of the performance. Again, every time when we deal with trying to get better designs, actually, regardless if you're an electrical engineer, a mechanical engineer, any engineer or scientist, we always have to measure metrics of performance, right? As mentioned last time. And of course, the most basic cache, the direct map cache. On Friday, it will be the two other versions, which are easier to discuss, and hopefully the discussion is less, or it will take within an hour. Okay, so recall from the five-stage pipeline RISC-V processor that I had before. Um, we treat our memory elements as normal read and write. Okay, but in reality, there is something peculiar about these memory elements because under the hood, or if you try to look into the details of these memories, they're actually pretty much complicated circuits. There is a memory hierarchy, right? But here's the thing. In our past lessons, we always assume that these memories are single cycle read and writes. Well, particularly reads are fully combinational and writes are controlled by the write enable signals, right? So that's how we treated them. They still work the same way, but right now we're going to stray a little bit and try to look into the, well, I wouldn't say it's non-idealities, but the better way of controlling memories. Okay. Now, there's a reason also because if you notice in our homeworks, these memories have very long latencies. I believe in the homework, I think the data memory or the instruction memory, both memories have around 200 nanoseconds. Now, there's a good reason for that. It's because of the decoding components. I mean, imagine you had usually a memory is probably around 1 gigabyte. Let's say that's a really small RAM, a random access memory. Now imagine you have to scan all the 100, not 100, but 1 gigabyte entries. That's a million entries. So that's the reason why some memories take long. In fact, in reality, some memory accesses, especially with memory hierarchies, they take multiple cycles. It's not just because combinationally they take long, but they also take multiple cycles, right? So that's something I have to take note of. Now we're gonna get into that in a bit. Now, some brief history. In the past decades, like that, it's 2022 right now, so maybe like almost 50 years, 40 years. Processors were built to be superbly fast. The race for producing fast computers, like computers, and take note, people like to use computers not because they are meant to be like personal desktops. That was like a side quest, but really, we wanted to make computers to solve engineering problems because computers, from the name itself, is a machine that computes mathematical or arithmetics, right? So people were very interested, researchers, scientists, especially people in the semiconductor industry. We were always trying to make processors to be very fast, right? However, one thing that they notice is that, hey, if you make the ALU very fast, then you'll have very fast processors. If you cut the logic time, then you'll always have very fast processors. Sure, yes, we're happy with that. But here's the thing. As processors started to go fast, at some point they became linear because of the power wall. If you remember last time, because the higher the speed, the higher the frequency leads to higher power. So it's gonna melt down your processors. But the problem is that okay, apparently it processors are very fast, but it looks like it's the memory bandwidth That's the one that's slowing down our processors. Right? Because if you think about it, most of the processing done is that you have to grab data from the memory. And that became a problem. And they figured that, okay, we cannot really utilize the 100% potential of our processors without improved memory. I mean, if my memory is slow but my processor is really fast, what's the overall speed up of my entire system, right? It's not really fast enough. We're limited by our memory. One good example is that, say, for example, you have your laptop or desktop, whether you use one with a hard drive, HDD, and then one with an SDD, you would definitely see that SDD speed up times are very, very high because you can boot up your computer in probably within 3 seconds only, right? Unlike in HDD, it's gonna take you what, a minute, somewhere in that range. Okay, so that's just a very brief history about this thing. Now, the first lesson that we need to discuss is about memory hierarchies. All right. So if you look under the hood and you go back to your processor, so this is your CPU, the same RISC-V processor. The first thing that we have is the set of 32-bit registers. 32-bit registers, right? And the thing about these 32-bit registers is that they're the ones that are directly accessed by our ALUs. Okay, sure, not a problem because you're just gonna have to read 32. You're just gonna have to decode one of the 32 registers, plug it into the ALU, and then you have the result immediately. Not a problem. Now, immediately after the ALU, if you remember last time, it's the data memory. But if you look under the hood of the data memory, you have three main components: the cache, the main memory, and the hard drive. Now, the cache, it's usually an on-chip thing. It's built with SRAMs, so static random access memory. Oops, I didn't put that there, but static random access memory. I hope you know what RAMs are. Uh, they are built to be small, okay, but they're very, very fast because the way you access them is that when your CPU tries to do a load instruction or a store instruction, it usually stores directly into the cache immediately after the CPU. Okay. This is the frontline interface between the CPU and the data memory. And because of the data transfer is really fast, or quote unquote really fast, it's around 200 nanoseconds, which is already approximately really fast. That's our definition of really fast memory. Right. So that's the first thing, cache. And take note, the only important part, it's made of SRAMs and it's closest to the CPU. But next to the cache is what we call the main memory, which is built with using dynamic RAMs. So caches are static, DRAMs or dynamic RAMs, dynamic DRAMs are an upgraded version in terms of having a higher, what do you call this, a higher storage of memory. Caches are like around 64 megabytes. Main memories are probably around a gigabyte or so. Okay, gigabytes. Okay. But particularly, the only way you're gonna remember RAMs is that these are the RAMs that you buy for your computers, right? So the main memory, quote unquote, main memory or the dynamic uh, RAM that you're using are the RAMs that you buy for your computers, for the laptops, for the desktops. Those are the RAMs. So they contain larger, around a gigabyte, 2 gigabyte, 4 gigabyte, 8 gigabyte, 16 gigabyte, right? Very big. But the RAMs are the SRAMs, the caches are really small. Okay. Uh, they pack more data, but they are slower because they're very capacitive. Later on, I'll show you what I mean by that. Now, the last but not the least is the hard drives, which are the largest. This one packs around like what, 500 gigabyte data, up to a two, or actually, if you go to the internet, you can get 4 terabytes right now. Okay, but they're the slowest, right? The reason why they're slow is because they are mechanical, right? Like magnetic disk drives. We do have SSDs, which are faster. It's equivalent, but I think I'm pretty sure the one that you're familiar with are the magnetic drives because that's the one that we use at least during our generation, right? Now they're really slow because it's mechanical. Magnetic drives are built using magnets. So this is their hard drive, and then you have a magnet here. Then you have this some sort of mechanical probe which reads and writes onto that magnet. So this magnet spins around, and then you're going to electrically reconfigure the data in here in the magnet with this mechanical probe. So it's really slow because machines are much slower than electrons, right? So it's really really slow. However, it's because of that we're able to pack in several data, and it's very cheap. Okay, so this is something that you have to take note of my memory hierarchies. So I'll go through very quickly through the cache and main memory, just so you know more about it. The circuits for SRAMs, for those who took CoE 197 under me, pretty sure, yeah, the two of you here have taken that up. Um, so circuits for RAM is that the way you treat it, it's just like any other memory, right? This is pretty much the memory that we're also using, at least on the block level or in the top level. This is how it actually looks like. So in Verilog or system Verilog, it's nothing but just a memory read. So you have the address, write enable. These two are just other control signals. Okay, the data that we put into and the data that we put out. Right, pretty much simple. But under the hood, if you look inside of it, is that you see a bunch of decoders. Well, the decoders are there to select, okay, which address do you want to access to. We have write enable registers or enable signal. Okay? And if you trace it back here, they are just literally from the name itself, write enable signals. If it's enabled, you can write on that row. So this is one row, one row, one row. Okay? And these are the columns in bits. All right. Now, I think this is supposed to be D in 0 and then D in 1. Hey, I didn't make that, so this is type. Oh, there's a D in 1 here pala, and then D in 0. This has to be D in 0. Okay. Anyway, now you have a bunch of decoders, you have a bunch of enable signals, and then you have these latches. Those latches, if you remember from your basic digital course, latches are your what do you call this? Your memory elements. Right. So if you look under the hood of a latch, it looks like something like this. This is what we call a 60 SRAM. It's called 60 because it has 6 transistors, right? If you count it, 1, 2, 3, 4, 5, and 6, right? So it's a 60 SRAM. I won't discuss the operations of it right now, but the only thing you have to know is that, okay, SRAMs have 6 transistors. That's quite expensive because that's so many transistors. And then you have to size them appropriately to be large enough to be able to store some data in this element. Okay. So this here in the middle is a feedback inverter, right? And then because of that feedback, you actually store a configuration if the data is a 1 or a 0, right? Now these things are super fast because it's not it may look capacitive, but it's not heavily capacitive. As you'll see later on when you compare it to DRAMs. And the way you'd access it is that you activate a word line. Then when you put a connection between these two lines, the bit line and the bit line bar are connections to probe. Okay, these are connections to probe. Okay, what's the state of the transistors or the inverters inside? Okay, so that's how memory SRAMs are actually built. Now, if I look at a much bigger picture, a typical SRAM system would look something like this, right? So if I grab one of this and then I compare it here, this is what it looks, and I stack them up together, this is what it looks like. Okay. So it's like you have several SRAM blocks or banks, right? Depending on the data that you're trying to look into. Okay. And then if you cascade them or concatenate them together, you can easily decode the data that you need. So this is just an FYI. I'm not going to go into detail for now, because it's more of a circuit thing rather than the actual high-level VLSI or top view of how we're dealing. Now the second part here is what we call the DRAM. The DRAM has the same elements, not a problem. But the circuit that you use to make a DRAM is just this. It's just one transistor. Okay, and that's the cool thing about it. It's because you only have one transistor, and then but you have a very large capacitor. Now the capacitor is large enough such that it can hold the correct data for around 1 millisecond. Right? Because you see the capacitors, they're not really ideal. They have resistive connections. Actually, they're quite connected to ground. So once you charge the capacitor, really, right? Once you put a charge in the capacitor, that charge suddenly seeps or leaks into the ground because of leakage. But then you see that the interesting thing about DRAMs is that okay, I can make a charge, I can store rather a charge up to a certain amount of time, but then I have to refresh it every now and then. But the nice thing about DRAMs is that it only consists of one transistor. The cool thing about it, it can be sized really small and with a longer length, only because you want to have the least number of leakage from the capacitor that's suddenly leaking into other components, okay, into other nodes, right? But then the thing is that, okay, if I want to store data, I'll just open the transistor, make a connection, and then I'll load the data here through the bit line. So if I want to put a charge of 1, then I'm going to load some charge 1 through by injecting some current into the capacitor. Now, if I want to read data, I just access the word line again, and then all I have to do is just, okay, I'm going to probe this node because there's a direct connection to that capacitor. And I'm going to use an amplifier, a sense amplifier to determine, hey, what's that data over there? Is it a 1? Is it a 0? That's it. Okay. It's so simple because you don't have any some sort of feedback circuit or so on. The only problem is that because the charge is leaking every now and then, is that you have to have a mechanic where you're constantly recharging the capacitor depending on the state that it's in. So they have mechanics, something like that. I won't discuss it here anymore. But the point is that it's only one transistor and one capacitor. The capacitor is quite large enough, but the thing is that you can actually pack a lot more data because of this, as opposed to having 6 transistors of the SRAM memory. Okay, so that's what a DRAM is. Now, going back to our memory hierarchies, so much about the circuit stuff. But it's not. It's important, but it's not part of our curriculum right now. It's really a more of a circuits class. But here's one very important thing that you have to know. This memory hierarchy, as I mentioned earlier, the closer you are to the CPU, the shorter the memory latency. Or in other words, your the accessing data is very very fast. Now, the farther you are, you have a longer latency due to many things. Well, particularly 3 major things. One is the decoding latency. The larger your circuit, the more logic gates, right? So between the cache, let's say hypothetically you just need 2 AND gates over here, because you're just comparing very few, or I don't know, very few data only. But the larger your memory, the more combinational logic you need in order to decode that data. Okay? That's one. The second one is that some of them have mechanical limitations, like the magnetic disk that I mentioned earlier, right? So that's really long. Remember, electrons travel faster than machines or mechanical machines. Last but not the least is travel time. And of course, let's say for example, between the SRAM and the DRAM, because you have larger decode circuits, you have longer wires. That's the tendency. And now here, the hard drive, since it's non-volatile, meaning you can take it out of your computer, put it in a different computer, you can still access the same data. You use a different interface over here, but then it's not on chip. It's a separate chip, like a SATA interface. Okay? And then that's a very long wiry thing before it actually gets into your memory or computer. Right. So there's this significant travel time through the wires. So point is, the closer you are to the CPU, the faster you are. The farther, the longer or the slower the memory is. Okay. And it's a trade-off: speed and the amount of memory. All right. Now here's the thing: SRAMs, as I mentioned, are faster, but they're far more expensive because, as you can see over here, they're faster but far more expensive because it contains 6 transistors. Right. Actually, in reality, right now, it's more than 6 transistors. Although it's a bit of a standard that it's only 6 transistors. People put in other control or built-in self-tests just to make sure the SRAMs are still working. Right. DRAMs are less, but they're really, really fast because they contain only 1 transistor each. Right. You can see that. Okay. They're not, but not as fast as SRAMs. SRAMs are like 10 times faster still. Now, SSD or hard drives, they are cheaper. They're the cheapest when it comes to memory storage. But then the bandwidth or the speed is really, really low. Right. It's so long. So that's a big, big trade-off. Okay. However, like I said, it's a trade-off between capacity and speed. Right. So because of that, people said, okay, we need to have a memory hierarchy because we need to get we need to have this nice trade-off between speed, capacity, and we have to find a way that it's actually operating really fast. Okay. Now here's the cool thing, the key technique is something that we call caches. So we'll be focusing our discussion on caches, all right? So the key technique to make memory look like it's faster is to introduce caches. Now caches are small memories mentioned earlier, but they have very fast read and write times. And the method for caching is actually a very good analogy to libraries, right? Wherein you actually work faster or study better when you have the necessary books on your table. Say for example, you go to engineering library in CS Lib or maybe in Melchor, um, and then let's say you have to study about CoE 113, right? And then the two books that I always put out in the reference, instead of getting one book at a time from the main library connection, and then you're gonna read it, why don't you put both books, right, into your working desk, and then you don't have to go around and look for your book in the main library connection. Right. I mean, if you remember during your elementary or high school days, we were also taught how to use the card catalogs. You know, it's the old. It's the we didn't really have internet yet back then, or maybe most of us did, but it's not really that good yet. Slow internet, so we still prefer to go to the library. You have this set of card catalogs over there. So those catalogs over there are the what they call the decoding part of our library because we're trying to find, hey, what's the how are the books arranged? What's the number? Where do you look? In what section, right? And your library collection is divided into different sections. Okay. Then once you get the book, you go to your table and then you study on your table, right? And then you as a student, you're the processor trying to study the things that you're doing. So again, instead of getting one book at a time, the idea of a cache is that the cache is your working desk. The thing is that why don't we get both books at the same time so that I don't have to go back and forth with the to the library collection, right? So that's how you do the. That's literally the analogy for caching. Now, as I mentioned earlier, there's a life lesson to this, but uh, actually, there's a good book here. I've noted here, "How the Brain Learns" by David Sousa. It's a really good book, an educational book for teachers. But whoops, hold on. Okay, I took out the trash earlier, but the truck is here. But anyway, so there's this very nice life lesson about memory, and then the good book about how the brain learns is that our brain is like a library too, right? So you in this part here, your environment are the inputs, the instructions of your processor, and then you have your immediate or the intermediate memory. Okay? So these are your registers, right? The idea is that the way we learn things is that we actually play around with fast very fast, uh, fast and then very slow memory. So, but in terms of spatial locality, it's like the registers are the data that we're trying to process at right now. Your working memory, okay, is essentially your cache. It's the things that you get from the library and put it into your desk. And then your long-term memory here is your hard drive, okay, or the main memory. Now, the thing is that how our brain works is that when you try to study uh, a topic, you try to recall lessons. Say, for example, going 112, your basic logic circuits, your basic, logic circuits, logic design. You're going to put all those data in your working memory. And for example, at this moment, you're thinking about those things because they're in your working memory. Okay? And then you're just trying to recall data from those past lessons. But then from your working memory, you're also using your immediate or your intermediate memory, which is what you're currently thinking right now at this moment. Like for example, you're trying to listen to me, you're trying to look at the slides and trying to read these things. It's your immediate memory that's working. So it's very close to how computers work, right? So you have registers, which is processing the current data that you're thinking of. And then your cache is the one that you access in your data memory. But then inside your data memory, you're also accessing data from a larger memory, whether it comes from the main memory or the hard drive. Okay. So the nice thing about it is that okay, this guy is not a computer scientist nor a computer engineer, uh, but he's a psychologist and a neuroscientist. And the very nice thing about it is that okay, memory essentially the caching method is very close to our uh, memory for learning. Okay? It's a good life lesson. And you can carry this over when you start working or later on, but being able to recognize that or catch yourself to recognize that, hey, this is how I'm actually learning. You don't really recall things all at once from the past, okay, from your long-term memory or from your library, but instead you're actually playing around this area because that's the one that you're currently trying to process. Okay, so just a good life lesson, and doing this with analogy makes it easier to understand caching. All right. So again, going back to caching, we studied about a bit more of caching about the details about caching, right? And the thing I want you guys to understand, and the way I try to rearrange this lecture is that, okay, I figure that it's easier to understand caching if you understand, again, the same thing that we're always saying is the data flow. And if it's not the data flow, at least the analogy of how caches are working. Now, caches need to store temporally and spatially recent data. Again, temporally is time, spatially is space. So we're gonna go about this next week, but as we go along, I want you guys to sort of recognize this temporal and spatial locality of recent data. Now, in the perspective of the CPU, again, what we're seeing is not the is the main memory, but the main memory actually consists of both the cache and the main memory, and well, whatever hard drive you put at the other end of it. But we're gonna focus here only on the cache and the main memory for now, okay? Because whatever is after the main memory, the concepts hold the same way. Or, I mean, they stay true. Okay, so this is what we call memory hierarchies. Um, yeah, okay. As mentioned earlier, these are actually cached. Oh, not this one, but rather this one. That's a wrong arrow. Okay, both instruction memory and data memory, they're actually cached memories, right? Not just data memory, but instruction memories as well, right? So right now, I'd like you to realize that, okay, when you try to look at RISC-V processors, or at least the basics of pipelines before, you can treat data memory as is, how we discussed them, a simple combinational read in a single cycle write. But then right now, I want you guys to stray away a bit from here and from the ideal memory implementations, and we'll look into more about the memory hierarchies. Now, one of the best first things that you have to recognize are the basic cache terminologies. And the easiest way to remember how caches work is to, uh, as I mentioned earlier, is that you have to memorize the terms first. So one of the first terms is the hit. When we say a memory hit occurred, it means that data exists in the cache. Okay, remember, the CPU is accessing data directly from the cache, not directly from the main memory. Okay, it's accessing it directly from the cache. But then, uh, okay, but then, for example, right? Let's say the CPU needs to access the data at address code beef. Okay. And then the CPU checks, hey cache, do you have code beef? The cache checks its contents. It's going to decode over here, and then it's gonna say, okay, yep, it's a hit. I have the data code beef because the code beef address is stored here in the cache. Take note, the cache is really small, okay, and the CPU doesn't care what kind of what's your the range of, or rather the CPU doesn't care what your cache contains. Okay? The only thing it needs to do is that, hey, it's gonna talk to cache and ask for data at the specified address. Now if the cache has that data, it's a hit. Then the cache replies, hey, it's a hit, and then you can get the data, and then the cache puts it back directly to the CPU. The other version is that, what if it's not in the cache? We call it a miss. Okay. Essentially, that's when the data is not in the cache, right? So the CPU says, hey, is I need the address at dead 1234. The cache checks, dead is not, the 1234 is not in my location. Hold on, I have to communicate with the main memory. And then the main memory is gonna look for that data. It's gonna take a long time because it's very long. Okay, and then once the main memory sees it and decodes it, it's gonna put it into the cache. Right. Now here's the thing. So the useful part about caches is that instead of the CPU directly asking the main memory all the time, which has a long time to search for that data, you're putting that data into the cache, okay, because that's what the CPU will get later on. Instead of accessing the main memory, why don't I access the faster memory? So, that's what happens in caching. And take note, it's a miss. If I don't find it in my cache, the cache has the penalty to ask the main memory first. The main memory sends it to the cache, and then the cache brings it back to the CPU. That's it. Okay, so hit and miss. Very basic concepts. Um, very useful to understand caches. Now we can actually have memory performances. For example, two metrics is what we call the miss rate and the hint rate, which are interchangeable from one another. Okay, so miss rate, it's literally the same thing. Okay, you get the total number of accesses. Let's say you're accessing from 00 up to, I don't know, FF something. Okay, get the total number of accesses, and then in those number of accesses, how many times did you miss? Okay, so it's a literal fraction. Okay. Now the miss rate over here, it's not like speed rate or something. It's more like a probability. It's a probability rate, probability rate. Okay. So from the name itself, miss rate, get total number of misses over the total number of accesses. Hit rate is 1 minus the miss rate. Okay. Actually, 1 minus the miss rate over here. Or you just get the number of hits over the total number of accesses. Very simple, right? Time check. Okay, we're going very fast. For example, suppose a program has 2,000 data accesses. Not a problem. Uh, we don't care if it's a load or store. All you have to do is a memory access. Okay. So 1,250 of those are of these requested data values are in the cache. It's a hit, and then the other 750 are misses. So simple math gives you 62.5% and 37.5% hit and miss rate respectively. It's very simple, right? So very easy to understand. Here's the thing. Sure, that's one metric or two metrics essentially, but quite interchangeable. The other metric is what we call the average memory access time or the AMAT. Okay. So the average memory access time can be understood very easily because it only composes of two things, right? One is the time it takes to access the cache. So that's a hit. And then the total time it takes to access the memory when it's a miss, right? So you have the remember, you have the CPU, you have the cache, and then you have the main memory, right? Main memory. Oop, oop. Okay. So the hit is just the time it accesses the cache. If the data is there, not a problem. And then the miss, okay, this two here is the miss, which should be multiplied by the miss rate because the probability that you're getting a miss, okay, times the time it takes you to get a miss, right? So it's and the miss is the time it takes from getting the data from memory, loading it to the cache, and putting it to the CPU. So that's the total T miss. Okay, so it's that simple, right? So it's a working equation. Now you might be wondering, why don't we multiply this hit rate with the miss rate, right? Well, because you already have the miss rate over here. You're assuming that for every time that you make a hit, there's a certain probability you're also making a miss. Okay. So it's already encompassed in this two, right? So that's why it's if you do the math later on, you can try it on yourself. But if you try to do the math for average memory access time, really the way you're going to analyze this equation is that okay, for every hit, there's an equivalent probability that I'm going to get a miss. So on average, for all the hits I make, all right, for all the hits I make, I can get a certain number of misses, right? And essentially, at the end of the day, that's my total memory access, my average memory access time, right? So very good example. Suppose you have a simple cache memory system, and then it takes you one cycle for a hit, and then 100 cycles for a miss. Okay, so this is in cycle time. Right? It can be in seconds, it can be in nanoseconds, it can be in cycles. All you have to do is like it's a concept of quote unquote time. Right. Now, say the current setup, the cache has a miss rate of 10%. The cache that I'm using provides that. What is the average memory access time? Simple, right? You add one cycle for all the hits that you're making on average, and then you multiply the how many cycles it takes on average when I hit a miss, right? Or not, I mean, when I make a miss rather. Okay? So you multiply 10% times 100 cycles. All in all, my average memory access time, if I have like an infinite number of data that I'm accessing, is around 11 cycles. All right, on average. So it's a probability thing, okay, or rather, it's a statistical method. Right now, it's useful because okay, it's a way to characterize how I would like to improve my my average memory access time, right? And it's very straightforward to identify what are the key metrics or the key components or specs that are actually affecting my average memory access time. It's the time to make a hit, so I can improve it by reducing the hit. I can improve my miss rate, and I can improve my miss time. So if I can put my miss time very low, it's very linear. Okay? And things like that. Okay. So average memory access time can also be used for multi-level analysis, right? For example, in our example, we were just looking at the main memory, but what if we also add the disk drive? It's the same thing, but this time we have this sort of chain rule that I'm pretty sure you guys need to how would you put it? You just it's just a matter of just trying to understand the equation of the average memory access time. So going back again, it's just a hit times the miss, and then this miss can be characterized to a better version, okay? Because that miss not better version, but also using a memory average memory access time. Okay, what do I mean by that? Say for example, in that CPU, oops, I'm gonna write CPU. I'm gonna write the cache. I'm gonna write the main memory, and then I'm gonna write my hard drive, hard disk drive, right? So it's the same thing. Okay? T cache hit times this in here is essentially the T main memory of the miss. So the main memory, the miss rate of the cache times the main memory miss, which consists of what happens if you hit from the main memory plus the miss rate from the main memory times the disk drive. Okay, I like it. You guys go back to the we call this to this lecture again later on. Replay the video. But the thing is that this form here is literally T hit plus the miss rate times the T miss. Okay. And then okay, that's what this entire form looks like, right? Whoop, including this parenthesis here. But this parenthesis in here is also in the form of a T hit plus the miss rate times the disk drive. Okay, so that's simple. Right? So you see, it's a chain rule. Okay, it's a literal chain rule that you're just cascading this or chaining this misses. All right, and it's pretty much the same thing. Okay, but take note, the first miss rate here is due to the cache because if you miss in the cache, then you have to calculate the time it takes to process the miss from the cache, right? And then inside the main memory, you make a hit, right? And then if it's not in the main memory, it has to access the disk drive, right? So there's a miss rate for the main memory, this guy over here, and then you're gonna multiply it to the time it takes for the disk drive. Now the disk drive, there is no hit or miss because that's the last stage of your memory. Okay, so one good example. Take note of that CPU, uh, cache, main memory, and the disk drive, right? So look at this, okay? So you have the cache, the main memory, the hard disk, the access time it takes, and then the miss rate that it takes, right? For each component. Now, if you actually calculate that, right, you just use the same equation. So the time it takes to make a hit is just 1. Whoop. What's the miss rate of the cache? 20%, right? Whoop. And then the total time, this take note, this is the T miss. I'm gonna write it down explicitly. T miss of the cache, right? And then this TMM hit here is okay. How many cycles does it take, or how much time does it take for me to access data from the main memory? Probably 50 cycles based on the data that was given to us. Okay, okay, that's a hit in the main memory. But then, okay, what if it's not in the main memory? Then you're gonna multiply the T miss. This is the T miss of the main memory, right? So you multiply the the miss rate of the main memory. Actually, the T miss of the main memory is this drive rather, but then you multiply the miss rate of the main memory, and then you multiply the disk drive because that's if it's not in the main memory, you have to access the disk drive. Whoop, over there. Right. So it's pretty much straightforward. If you do the math, it takes you 13 cycles. Okay. Now imagine going back again, right? CPU, cache, main memory, and then the disk drive. If the cache and the main memory are not there, and you're accessing data directly from the disk drive, what happens is that you're always, just to access one data, you have to spend 100 cycles. That's not good, right? That's so bad. If you put the main memory and the disk drive all together, possible, not a problem, okay? But how many cycles does it take? It's this component over here, right? That's 50 plus 10 cycles. That's like 60 cycles. That's still so bad, right? It's not so good. It takes 60 cycles for me to access data on average from, if I only have the main memory and hard disk. But if I put my cache in between them, which greatly reduces the miss rate, okay, of, or rather, it's because of the miss rate affecting this entire 60 cycles, I have a total of 13 cycles only on a miss. Okay? On average, I only need to spend 13 cycles as opposed to 60 or 100 cycles. So that's extra saving. This is why memory hierarchy is very, very important. Okay? So yeah, that's a very important lesson there. Time check. Okay. We're going. Aha, we're going too slow. um, so again, performance improves because of the reduced miss rate and the latency times. Now, miss rate and latency times are trade-offs. Okay, because remember, from the CPU, I'm just gonna write time from the CPU to the cache, which is a much bigger scope. CPU is small, cache, and then the main memory is a little bit bigger, and then the disk drive is, yeah, it's holy cow big, right? The smaller the cache, the faster the latency, right? But the miss rate increases. Why? Because if there's a chance that the data does not exist in the cache, so you have to access in the other memory elements. But the larger the cache or the larger memory elements that you have, not a problem. The slower the latency, but because you have to decode so many things, but the miss rate decreases. Okay. So that's something you have to think about. It's a trade-off, miss rate and latency times. Now, the second part for discussion, I'll try to speed it up, but today we'll try to understand a bit more of the architecture of the caches. And again, the technique is really to follow the data flow. And we're going to study the basic one. Here's the thing. There are basic cache terminologies. And again, the idea is to memorize the terms. So we have the concept of capacity. You have a cache, and then there's a certain number of words that you can store. The total words that you can store is the capacity C. Okay. Now, each cache contains sets. So every time you access an element in the cache, that's one set. Okay. Now, each set can contain one or more blocks. Okay. By blocks, meaning, maybe one set could be two consecutive data, or maybe one set could be four consecutive data. It depends. We specify that, but we're gonna get back to that next week. And then note that each block contains some block size B, which is the number of data elements that are contained in a block. Okay, I mean from the name itself. Okay, so the total number of blocks is, you have to grab all the contents and then you divide the number of blocks within a block set. Okay, actually, maybe this S and B are quite interchanging. What you call it, the set or the block set, right? As you'll see later on, or next week rather. Now, mapping is a term that we use to determine, okay, from the main memory, I'm going to overwrite that, from the main memory into the cache, there's a certain translation from the main memory address to the cache. So that's what you call a mapping. Okay? So one basic cache. Suppose we have a cache here that has a total of 8 words only. There are 8 blocks. There are, okay, for now, let's accept that each set contains one block. Okay? Because each block is just contains one word each. Okay, so this is one word. It's like 32 bits. So let's set it at that first. So one set contains one block because one block contains one set, one word each, which is 32 bits long. That's simple, right? It's that simple. This is our cache. We only have 8 elements. We're in from the main memory, right? I'm gonna put data in here. Okay. Now, what you have is that your main memory can be 2 to the 32 bits long, or rather 2 to the 30 bits or 2 to the third can contain 2 to the 32 elements. Because your main memory, it's very, very large. That's the idea, right? So from 0, 0, 0, 0, 0 up to, this is in bits, all right, up to 1, 1, 1, 1, 0, 0. And if you remember last time, we skip count the by 4, actually, only because we have to be word aligned. One data, if you remember last time, right, the memory is byte addressable, but we have to be word aligned. So we skip count by 4. So 4, 8, C is 12, 16, 10, 20, and so on and so forth. We are skip counting by 0, 4, 8, and so on. Yeah. That's simple, right? So the first 2 bits, they're always 0. This is what we call the byte offsets. Okay? They're always 0 because we're skip counting because everything needs to be word aligned. Okay? So we'll modify that a bit. But the idea is that's the thing that you have to take note of. That we're always skip counting by 4 because it has to be word aligned. Right? The second part is that the next 3 bits will be your set bits, right? Or rather, the ones that tell you, okay, that's the mapping from the main memory address into your cache. Okay. So again, the first 2 bits is the byte offset because you have to skip count by 4. And then the next 3 bits, we're going to use those bits as my mapping from main memory to set bits. Okay. So what does that mean? Okay. The crucial concept is that those set bits are the ones that tell you, okay, if I'm gonna store data, store access, or rather, let's just say store or load as a single access, right? If I'm gonna access data in this address, the 11100 FFFFC, okay, because the next 3 bits after the byte offsets are 111, I have to put it into the 111 part of my cache, right? I have to put it there. And then, in the case of the FFFF8, if you put that in binary, it's like 111100000. Skip the next first 2 and then grab the next 3. Those things I'm gonna map them directly into 6. Okay. Parang nagalaw ang aking figure. This one has to point here. Okay. This one, it's the 111. It has to point here. This is correct, right? So basically, you just need to look at the next 3 bits after the byte offset, and that's the mapping from the main memory into the cache. So if I want to access this address, I'm gonna put that data into my cache in that set bits of the cache, right? And the other example, for example, 0000, everything is 0. The next 3 bits are 0. Those are the set bits. So if I'm gonna put data or access this data, I'm gonna put it in the set bits 000, right? And it's gonna be in here. So this is what we call a direct mapping, because for every address, there's a direct mapping from that specific address to a specific location in the cache. It's that simple, right? It's always that simple. Okay, is that clear? So it's but I don't know how else to explain it, but it's like there's a rule, or not a rule, but a convention, or how do you put it? At least this is how we are all taught about how to use this caching, okay, for a direct map cache. Again, the next 3 bits, depending on the number of elements in your cache, right? That's what you're gonna grab and put that mapping from the main memory into the cache. Okay? Now, for the given cache, we need to somehow specify the entire address. Right? Because how do we know that that data over here, okay, belongs to either FFFFC or DC or I don't know 0001C? How do we do that? Okay, we need to use all the remaining bits, all the remaining upper bits as my tag bits. Okay, because it needs to be part of the quote unquote cache address, right? Because essentially what you want to do in the cache is that you want to it's like how would you put this? The best term is that you're trying to compress the memory into a smaller memory. Okay. So this is the way you're quote unquote compressing memory. You're directly mapping depending on the set bits, but then also you're also going to have to get the tag bits to indicate that hey, that data in here actually belongs to the real address up here. Okay. the real address in the main memory. Okay? And the thing is, it's a lossless compression because you can put it into the cache, and then you can directly recall where it actually belongs to the main memory. Okay? So the tag bits identify the certain where if a certain data is in the actual cache. Right. So that's the tag bits of here. Set bits tell you which part of the cache you have to belong to. Tag bits are things that you're gonna grab here. So technically speaking, I have to redraw this because uh, since the set and blocks are the same thing, I could replace that block with tag bits. Okay. And I'm supposed to show that, hey, you're gonna grab all the remaining upper bits. But in a different way, okay. So if you have the main memory address of your main memory, time check. Whoops. Yeah, we're gonna overtime a bit, but you're almost done. Um, if you have your main memory address, you're going to slice these bits. Okay? So if you have a capacity of 8, right? The same example that we're using, right? If you have 8 element entries, and then you need 3 bits, okay, to determine the set. Okay? The way you're gonna slice the main memory address is that, okay, you have to cut the byte offset because again skip counting by 4. Get the next 3 because that's the one that you're going to control or map. Hey, this memory location, main memory address location needs to belong into this cache location, right? But then you're also going to grab the main memory address, the tag bits of the main memory address, which is everything above the set codes or the set bits, right? So what you'll do is that you'll have the set bits, you're gonna have the tag, and then you're gonna have the data. Okay. You're gonna grab the tag, you're gonna grab the data, you're gonna use the set to select which part of the entry, and then you're gonna put everything there. So such that when I try to recall the data or check if the data is there, we're gonna check first the set to determine, hey, which data we're gonna look into, and then we're gonna check the tag to determine, hey, which memory address are you actually pertaining to? Okay? So that's the thing. So the tag is the one that actually tells us, are you a hit or a miss? Okay. Say for example, right? I want to write the data, whatever the data in the main memory here in the FFFC into my cache, right? So again, grab that 2 bits byte offset, ignore those two. Right? You just know it's you're not gonna use it anyway. You're gonna grab the 3 bits for set bits, okay? And then you're gonna use the tag bits, you're gonna place it here in the cache also. So the tag bits is also quote unquote the cache address. Actually, I have to swap this thing because technically you're also loading the tag bits in here, right? Such that if I'm going, again, if your CPU is going to access from the main memory, or rather the memory, we don't know because again the CPU just sees one memory, doesn't really know the hierarchy. If the CPU sees the main memory or the memory, all it has to send is that, okay, I need to get this address. The CPU is going to send the address. And then what the memory will do is that, okay, we're gonna grab we're gonna grab the set bits. I'm gonna look into the set bits, and then the next thing I'm gonna do is that I'm gonna check the tag, which is the remaining upper bits of the address. If the tag and that address are equal, then I generate a hit. If they are not equal, I'm gonna make a miss. Okay, it's that simple. Okay, and it's very useful because, for example, let's say I loaded this FFFC in the memory. Okay, so it's the tag and then it's the set bits. But then my CPU is going to access. Let's see who's the 111 here. This one, DC. Right? I'm gonna access DC. And it's also pointing to the first 3 bits. It's also pointing here. Not a problem. Okay, I'm going to check that. However, if I'm going to look at the tag of DC, and if you look at over here, the LSB, or the least significant bit of the tag, is a 0. But the tag that I have here, because the one that I stored is FC, right? The current data that's stored is FC. But the tag that I'm looking at is a 1, right? It's a 1. But then the one that I'm trying to access is a 0, has a 0 in the LSB. So it will be a miss, indicating that, oops, the data that you have is at this address, DC, is not in my cache. Then I'm going to have to process my miss penalty, and then I have to replace this tag as a 0 later, and then I have to replace this data as a DC. Okay? So that's basically the basics of a cache. It's very simple, right? Now, the important lesson here is really two things, right? How do you slice the memory address? Where's my, oops. How do I slice a memory address? Slicing. And determining, actually, that's it, right? That's pretty much it. How do I slice it? And then what do I have to look into? Again, the set bits, the next 3 bits, are those that refer to the set bits that you're using. And then the tag, the upper bits that you're not using, are those that refer to the tag, right? It's the one that tells you if it's a hit or a miss. Okay. Now here's a challenge now. What happens if the total capacity is 16? How many bits are you gonna use for the tag, and how many bits are you gonna use for the set and for the offset, byte offset? All right. If it's 16, you have 16 entries down here, right? Then you need 4 bits for the set code, because you now have 16 entries. You need, right? You need 1111, 1110, dot 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 dot. Okay, until you have all 16 entries. So you need 4 bits for the set. The byte offset is still just 2 bits, because we're still skip counting by 2. Not a problem. Now, if you have 2 bits for the byte offset, 4 bits for the set bits, because you have to select among 16 entries. So that's 6 bits in total. So, okay, 4 bits for the set plus 2 bits for the offset. That's 6 bits in total. How many bits do you need to use for the tag? Since it's the upper remaining bits, right? So and our address is just 32 bits long, minus 6, you need 26 bits left for the tag. Okay? So that's simple. Okay, one very quick example. Find the number of set and tag bits in a direct map cache wherein you have 1024 sets. So that's 2 to the 10, right? So you can imagine, right? Now the address size is still 32 bits. So a cache with 2 to the 10 or 1024 entries just requires 10 bits. So you could imagine that this is your cache. You have 1024 entries. You need 10 bits to at least access one entry, right, in total. Okay. The least significant 2 bits of the 32-bit address are still the offset. So you have a total of 12 right now that you're going to use, 10 for the set bits and then 2 for the offset. And then, of course, you have 32 all in all. You have to subtract both of them, right? You need 32 all in all, subtract both of them. That leaves you to 20 bits for the tag, right? It's very simple, right? That's it. Now, as cache increases, you'll notice that as cache increases, the number of bits that you need for set increases as well. Okay? The set bits increases, but the tag bits decrease. Right. So is that a trade-off? It will be a trade-off, okay? Because you're trying to balance how many. Again, the larger the cache, the longer the decode time. Right. That's what they're trying to trade off. So last concept. I can finish in 10 minutes. Okay. Last concept. Caches actually have to add valid bits as well. When you start up a machine, right, when you start up your computer on reset, your memory has gibberish. Okay? You don't. Some processors or some technologies clear their memory to 0, but in reality, when you start up your memories, they're all gibberish. You have mixed ones and zeros. So the data that you have is what they call the garbage data, not gibberish data, but garbage data, because they don't mean the same anything at all when you start up a processor or a computer. Okay. So what they do is that they have to put valid tags or valid bits. Okay? And the idea is valid bits is that it's initially 0 when you start up. This is the only thing that you try to clear in the memory. Instead of trying to clear everything in memory to 0, what you try to clear instead is just the valid bits. Okay. And then, you know, the moment you start putting data on that tag, right, or rather, if you start putting data on that memory or that cache location, it becomes a valid bit, right? And then that means you have meaningful data. So the non-meaningful data means garbage data. So now here's the thing: if data exists both in the cache and the memory, you have to specify that, hey, this data exists both in cache and memory, and you set the valid bits for that. But take note, the valid bits only exist because of the startup sequence. right? To tell them that, because what if suddenly you it so happens that your tag and set bits, or rather the tag bits that you put in your memory is correct, but on startup, or rather on startup, the tag bits on memory was actually correct, and then you start accessing data from the cache, but then it was garbage data all this time on startup, right? So you have to make sure you had the capability to verify, hey, that data needs to be valid. Okay? So they add the valid bit. This is for startup components only. Okay. So one good example, let's say on startup, you have these things, and then you have gibberish data over here. Right? The tag bits are also gibberish. Okay. And then suppose that we start accessing 0x4, C8, 4C8 in sequence, right? So we're gonna access 04. 04 has if we're gonna write it down, actually if I'm gonna write down the last 4 bits now, right? 0x04. That's like, or rather, no, just the last 4 bits really. For 04 is 0010, right? Um, and of course, 00, sorry, it's not that. It's 0100. The first 2 bits are the byte offset. Okay. And then the next 3 bits, so of course, anything trailing ahead or before are zeros. So the next 3 bits are 010, 001 rather, right? So if I'm going to access 0x4, I'm going to put it in 001 because that's the set bit, 001. And then the trailing tags are just 000. Not a problem. I put the data there. If I'm gonna put onto C, C has okay, so 0x0C would be 0000 underscore 1100. So byte offset, set bits 00011, right? C8. Okay, so C8. Oh, I did not put that in order. I messed up that order. It has to be, let's put this as 8 first, and then this is C, and then 8 first, then this is C. Right, so going back, this is Z. 0x08 would be 1, 2, 3, 4, 1, 0, 0, 0. So byte offset, and then the next 3 bits are 0, 1, 0. So if I'm going to load onto cycle 3, 0x8, I'm going to access 0, 1, 0. The tag bits are all 0 at the beginning. And then if I'm going to load onto C, I'm going to put the tag bits there. The C is 0, 1, 1. Okay, and then the tag bits are all 0, 0, not a problem. Whoops, this has to be a 1. Why are there so many erasures? Erase. Oop, pen. So this has to be a 1. Okay, so every time, upon startup, everything is gibberish. But every time I'm starting to load, I load the data, but I also update my valid signal. Okay, and consecutively, it's the same thing. Now, on the second cycle that I'm accessing X4, X8, and XC, and because the data exists in my memory already, okay, I don't have to, it's not a miss because the data is already in my cache. So that's not a problem. Okay. So the second time, all are the hits. Okay. So here's another example, the last example actually, time check. Okay. Find the total number of bits for a direct map cache with 1024 sets. Same thing a while ago. But this time, the cache also has valid bits. Right. So when you come across questions like this, it's asking for the total bits for the quote unquote cache addressing and the data that you're storing. So in total, you have 10 bits for the set bits, you have 20 bits for the tag, and then 1 bit for the valid. Right. So that's and then you also have to include 32 bits for the data that you're storing. So if you add all of this, that's a total of around 31 plus 32 is around 63 bits all in all, times the total number of entries. Because it's a total number of sets, right, that you're using. So times 1024, you need a total of 63 kilobits, or whatever that equivalent is. Okay? So that's pretty much it for the, it's a very simple example. All you have to do is just draw it and then map it up. All right? Good. So in summary, memory hierarchy improves memory performance. We learn how to compute the average memory access time. That's the second component. Basic cache terminologies, basic cache structure. Next week, we'll discuss about set associative and fully associative caches next meeting. Hopefully, that time is much, much shorter. Actually, yeah, I think we hit around an hour. Okay, so references and so on and so forth. Any questions? I know it's a lot to take in, but actually, it's better to read this that rather than me discussing it. It's like better to demonstrate and show the readings instead. Okay. Any questions? No questions? Sir, are sets physical slots or just uh, virtual spaces? Okay, for caches, these sets here, that's a good question actually. These sets here are physical slots. Okay, because in the direct mapping, we are literally actually that's a good question. Is it actually a virtual space or a physical space? I have to okay. I'm not sure what's the proper way to think about it. I will answer that next week or in the next week after reading break, just so that we are in agreement what we mean by a virtual space and a physical space, right? But the way I treat these set bits is that in the hardware perspective, and if you're looking into the cache controller, it's a physical space, right? Because say for example, I'm gonna use the shorter picture here. The way I'm gonna treat it in respect to the cache controller perspective, it's a physical space because it's a direct space for the cache, right? So if I have a cache controller here, cache control, right? Take note because the one who's assigning really where you put these things is in the cache controller, right? It's like some kind of extra mechanic or extra controller or decoder that tells you, hey, you put that data in this specific location, right? You put in the main address. You put in the cache controller. The cache controller dictates or multiplexes where in this cache do you put it, right? So in the perspective of the cache controller, it's a physical space. It doesn't care, right, whether what kind of data you are. The only thing it knows is that, okay, if you give me this main memory address, I need you to put it here. So for the cache controller, it's a physical space, right? But maybe in the perspective, in the overall perspective, not necessarily just the CPU, because again, the CPU doesn't care whether which data is in the cache, right, or the main memory. Don't CPU only cares that, okay, I give you my main address, you need to give me the data. But in the perspective of the overall perspective, it might look like a virtual space because essentially what you're saying is that, okay, in this set over here, every data that ends with the 111 needs to be here. So it's like a quote unquote a virtual space. In the perspective of the CPU or the user, it's like, okay, I just know you exist here, right? That's why it looks like a virtual space in that perspective. Okay. So that's a very good question. I'll get back to you on that when we talk about virtual memory next time, just to make sure I have to review it just to make sure and make sure that okay, what's the real or how do they conventionally define virtual and physical spaces? But that's a good question. That's a very very good question. Okay. Anything else? Okay, fantastic. You're asking very good questions, Tim. Okay, I like it. Other questions from the others? Wala? Okay. I'll stop recording here.